Hey everyone, this is lesson 7 in unit 7. We're looking at partial fractions today. In this lesson, we're going to learn how to rewrite rational expressions as the sum or difference of two partial fractions. Here you can see this right-hand side is what we call the partial fraction decomposition. And together the whole thing makes up the partial fraction decomposition. So 4 things you need to know when you're looking at decomposing fractions is, first of all, if you have a numerator power equal to or greater than the denominator power, you're going to need to divide the denominator into the numerator to have a polynomial plus the remainder over the denominator. Next, you want to factor the denominator so that you have it completely factored in terms of linear factors and quadratic factors. And if you get a quadratic factor, make sure it's irreducible over the real numbers, such as when you have the difference or the sum of cubes. Also, when you're writing the linear factors, most textbooks are using these a sub 1, a sub 2, a sub n. I would rather use constants like a and b and c until you get to the end. Okay, just remember that the power in the denominator is larger than the power in the numerator. So when you have quadratic factors, you have to take that into account. And without too much discussion, I'll show you what I mean when we get there. As an example, we'll model it. And here there's 5 things that are kind of a procedural guideline for you. But like I said, if we model it, you'll catch on. And I guess the most important thing is, why am I learning to do this? Because when we get to calculus, there's an operation called anti-differentiation when you need to find an integral and you have an improper fraction like this. We have to use partial fraction decomposition. So in this first example, this is a pretty easy lesson. In the first example, my factors for x squared plus 4x plus 3 are x plus 3 and x plus 1. And to get that partial fraction decomposition, you would take those 2 linear terms and we would need a constant up here and a constant up here, because this would be like x to the 0 power, where my degree in the bottom is larger than my degree in the top. Okay, so I'm just going to use the constants there. This one, if you factor out an x squared, we're going to have x squared and then x minus 6. So we got to think about those factors. We would need first the linear term and then a number, so that the numerator power is smaller than the denominator. And then we could also have an x term, or we could have an x squared term. Now this is where it gets tricky. Here I could have a b value here, but over here I need a c with an x, and I possibly could also have another constant added to it. We just don't know unless we went to find that to see what happens there. But like it said, don't solve for the constants in this case. Just get the habit of setting them up. So this will be the first one, and there's 2 rules of thumb. You either want to use the system of equation method or the Heaviside cover-up method. I prefer the second one, but I want to work at least one with the system of equations so you can understand how that goes. So in this case, factors of the denominator would be x plus 5 and then x minus 2. And both of those are linear, so I need a constant plus another constant, and they would have to add up together to give me that left-hand side of the equation. So using systems of equations, the first thing I'm going to do is clear the denominators. So if we multiply all the way through by that denominator, we'll end up with 5x plus 4 is equal to a times x minus 2 and b times x plus 5. So distributing the right side, we have ax minus 2a plus bx plus 5b. And then we can group together terms on the right side so that the x term is a plus b. And then we have 5b minus 2a, or negative 2a plus 5b. And by the system of equations method, if we look at the left side, this 5x has to be equivalent to this term here. And the 4 is going to be equivalent to the rest of our equation. So thinking about that, the system of equations says that a plus b has to give me 5, and negative 2a plus 5b must equal 4. So this is our system of equations. And using that idea, if a is equal to 5 minus b, then we can substitute into equation a, and negative 2 times our substitute for a is equal to 4. So negative 10 plus 2b plus 5b is 4. So 7b is equal to 14, and b is 2. And if b is 2, then a must be 3. So the partial fraction is going to be 3 over x plus 5, and 2 over x minus 2 is going to equal the original problem, 5x plus 4 over x squared plus 3x minus 10. So this is my partial fraction decomposition there. These two rational expressions combine and simplify to that. So that was the system of equations method. Next, we'll look at the Heaviside cover-up method. Doesn't always work, but when it does, it makes everything easier to me. Factoring the denominator, we could have factors of x minus 3 and x plus 2. Or x minus 2, I'm sorry. We need a positive 6. So we need a constant there and a constant there. Then clearing the denominators, multiplying through by that quadratic, we'll end up with a times x minus 2 and b times x minus 3. So the Heaviside method goes something along the lines of this. If I let x equal 2, this entire term has gone away, right? So we could allow that to happen. So let's say we let x equals 2. Then you have 6 times 2 minus 14 equals 0. And then a 2 here is going to give us negative b, because 2 minus 3 is negative 1. And then 12 minus 14 is negative 2, so b is positive 2. Then, using that same kind of logic, if we let x be 3, we could cover up that side. So by allowing x to be 3, on the left-hand side we have 6 times 3, that's 18, minus 14. And if we put a 3 here, that's going to be equal to a. So a is 4. And then replacing the unknowns with a 4 and b 2, this is our partial fraction decomposition. So I really prefer the Heaviside method when it works, and we can use that. Here's one with an x squared minus 1 term. So we have the difference of two squares, x plus 1 and x minus 1. And first I'm going to clear the fractions. So we only have an equation with no denominator. We have a times x minus 1 and b times x plus 1. And again, I'm going to use the cover-up Heaviside method. Heaviside was a mathematician, I believe. So if we let x be 1, then this term has gone away. And we have on the left-hand side negative 2 times 1 minus 8. So that gives us negative 10. And putting 1 there, we have negative 10 is 2b. So b is negative 5. And then if we let x be negative 1, then this term would disappear and give us a 0. And on the left-hand side, we would have positive 2 minus 8. So that would be negative 6. And on the right-hand side, that would give us negative 2a. So positive a is 3. And then back to our original problem, if positive a is 3 and b is negative 5, I can change this to minus if we want, or you can leave it plus and put the negative up here, either way. So you have your partial fraction decomposition. So this is not a hard thing. You just have to be careful with the arithmetic and the algebra. Here, if we factor correctly, we're going to have x and then x squared plus 2x plus 1. So that's a perfect square trinomial. So our factors are going to be x, and then we could have x plus 1 or x plus 1 squared. So we've got to consider it could be that with a number, or it could be cx plus 1 over x plus 1 squared. Just have to solve it to find out whether that b is a 0 or not. Let's see, so we want to clear the fractions and only have an equation to relate. So 3x squared plus 12x plus 4 multiplied by the denominator. The denominator cancels that. And then this times that denominator is going to give us a times x plus 1 squared. And then this is going to be b times x times another x plus 1. And the c already has both of those factors, so it needs another x. So c times x. Let's see, we got to give this one a cx squared. Now, using the cover-up method, let's say if we first of all let x be negative 1, then we're going to get rid of the a's and the b's. They're both going to be eliminated because negative 1 here would mean 0 times a, and negative 1 here would be gone as well. So if we let 3 times negative 1 squared plus 12 times negative 1 plus 4, and negative 1 squared times c would be c. So this is 3 minus 12 plus 4, that's negative 5. C is negative 5. Next we want to if we let x be 0, let's take a look at that. If x is 0, this is gone, and this is gone. So allowing x to be 0, on the left-hand side, we got 0 plus 4. So 4 is equal to 1 squared times a. So 4 is equal to a. And then the third thing we can do is we already know a is 4 and c is negative 5. So if we substitute and let x be 1, when we know a is 4 and c is negative 5, then we have 3 times 1 plus 12 times 1 plus 4 is equal to A times 1 plus 1 squared, and C is, let's see, 2 times, I gotta uncover this, I can't see it. We got 1 plus 1, so that's 2 times 1 times B plus 2B, and then C was -5 times 1, so -5. And that should just about get us done. Here we got 12 and 7, so 19 is equal to 16 plus 2B minus 5, so 16 minus 5 is 11 from 19. That's going to give us 8 is 2B, so B is 4. And then our partial fraction decomposition to get that 3x squared plus 12x plus 4 over that cubic 2x squared plus x would need A is 4 and B, what was B? B was 4 for x plus 1, and C was -5, so we'd have a plus -5 over x plus 1 squared. So here's our partial fraction decomposition. Ooh, that one's a tough one. And then example 6, write the partial fraction decomposition. We've got the difference of 2 cubes. So we have an x minus 1 for the denominator of A, and then we have an irreducible quadratic factor of x squared plus x plus 1. If you remember that pattern from Algebra 2. Clearing the denominator, we have 3x minus 9 is equal to A times the quadratic plus bx plus c times the x minus 1. And in this case, we'll let x be 1. So 3 times 1 minus 9 gives us -6. And if x is 1, this entire term has gone away. So we got 3a, -6 is 3a, so a is -2. And then about the only thing left we can do is to substitute what we know here. So let's get rid of this. Oh, not that way. Let's get rid of this way. So we can substitute 3x minus 9 is equal to, let's see, a is -2, so we're going to distribute -2 to these terms. -2x squared minus 2x minus 2, and we have bx plus c times x minus 1. So I'm going to leave those there a minute and clean this up. Let's see, we've got 2x squared, we'll take all the terms over to the left. 2x squared plus 5x minus 7, I think that's going to factor 2x plus 7 times x minus 1. Oh, how convenient is that? Because we have x minus 1 here, so we can cancel or eliminate that common factor on both sides. So we don't need this and we don't need this. And this will be pretty easy. So 2x plus 7 is equated to bx plus c, which tells us 2 is b and 7 is c. So if b is 2 and c is 7, then our partial fraction decomposition for 3x minus 9 over the difference of 2 cubes is, what was a? -2 over x minus 1 plus 2x plus 7 over the quadratic x squared plus x plus 1. So partial fraction decomposition. We have one more to go. So the last one is, let's see, we can have x squared plus 1, and we need a power less than 2, so ax plus b, and then it could be x squared plus 1 squared, so a power less than that would be cx plus d, because this power is quadratic, so we need a linear factor. And then clearing the denominator, x cubed minus 2x squared plus 3x plus 1 would be ax plus b times x squared plus 1 and cx plus d, and that's it, times x squared plus 1 cancels. So that's all good. Don't need that extra parentheses. Let's see, I don't think we can, we can't use the cover-up method here because nothing other than 0, but that doesn't really help. So let's distribute the left side. We've got ax cubed plus bx squared plus ax plus b plus cx plus d. And we can group ax cubed and bx squared, and the x terms are a plus c is equated to the x term, and then the b plus d is our constant. So if we equate those coefficients, I'm going to make a little note here, equate the coefficients to the left side, then a is 1, because that's our cubic term, and b is negative 2, that's our squared term, and then the linear term, a plus c, is 3, but a is 1, so c is 2, and then b plus d is 1, b plus d is 1, but b is negative 2, so d is 3. And the partial fraction, I'm just going to write the partial fraction on the right side that's equivalent to the left side, would be x minus 2, because a is 1, over the x squared plus 1, and then bx, or cx plus d, cx plus d would be x squared plus 1 squared. So this is the right side, the two fractions that add up to the biggest combined fraction. And that's the end of Lesson 7, Partial Fractions. See you next time.